So, let us look at the derivatives now. So, what we want to find out is to minimize this error, right. This should be E t. So, in order for us to find the smallest value of the derivative of E t, we have to do the derivation for all the parameters that we are looking at, d v or rather v, w and u, right. So, let us start from the first parameter v. Okay. So, we want to find out what is the change that we want to make when there is a error that coming from the output layer. Okay. So, I have listed this for our convenience. Let us look at dou E by dou V. Okay. So, we are taking this error at state t, right. So, we have dou E t by dou V, which would be equal to. So, we are going to be finding the error with respect to y t, right. So, we have dou E by dou y t, and then we are going to be finding this y t with respect to z t, okay. And then we are going to be finding the change with respect to v. So, it is a chain rule that you can apply, wherein you will have this dou E t here, and then here you will write dou y t hat by dou z t, and then here you will have dou z t by dou v. So, we have to find these values individually and then multiply that, you will get dou E t by dou v. Okay. So, we know that when we differentiate with respect to this, okay, so this is nothing but changing this value, right. So, if you use a mean square value, this is going to be y minus y hat, or it will be 1 by y if you are going to be using a cross entropy model. This becomes 1 because we are going to be using a one hot vector. If you use one hot vector, this will become 1, otherwise it will be y t. Okay. Okay, so, let us not really worry about what we are going to be taking at on the right side. So, we will just have the notation for that and then use it in the computation of the derivative for v. Okay. All right. So, what we have done here is, we are going to be taking these two and then calling it as delta out t. So, this is going to be the loss for each of the units in the output layer here, okay, for each of the units in the output layer. So, we call it as delta out t, and then when you differentiate this, when you do the partial differentiation of dy t by dz t, what do you get? Oh, I am sorry. So, this is what we are calling it as delta t out. So, we are going to be doing the partial derivative of dou z t with respect to v. So, what you get is s t. So, the error with respect to the value here is delta t out into s t, all right. So, this is the derivative for v. And then now let us look at the derivative for w. It is in the similar fashion, we are going to be using the chain rule to find out what is the change that we require, so that we can update w with that particular chain. Okay. And this is the chain that we want to find out, with using which we will update the w. Again, use the chain rule. When I am going to leave this to you as an exercise to find out how these values are obtained. So, in this case, I am not completely changing these values, I am just using sigma dash. This is a derivative. Okay, I am just leaving it as is. So, if you can actually expand when you want to write your computer application using this. Okay. So, dou E t by dou W is obtained using the chain rule, and then the value would be delta T out V sigma dash of H t and x t. The x t comes from here. Okay. And this is what you get from dou S t by dou S t, what you get from here. So, you may want to expand this and then see what the actual value is. Okay, let us move on to the next one. So, now we have to find the derivative with respect to u, so that we can update the matrix u here. So, again apply the chain rule. So, we are going to be getting values similar to this. Okay. When you are doing the back propagation, you will notice that this particular state depends on the previous state, right. So, there is some contribution that is coming from the previous state. So, we need to make sure that the value of the previous state also is included in this particular computation. So, that is what I write here as delta next. Okay. This value will turn out to be this, and this needs to be added to dou E t by dou u. Okay. All right. So, when I unroll this, okay, we have done only for one small piece in the RNN. So, now we unroll it. So, now this is how the entire network looks. Okay. So, we have from the timestamp of 1 to time slice t. Okay. So, we have all these states now available. So, how do you do the back propagation in this case? So, we have done it for one, now we have to see how it can be extended for the entire stuff. So, since they are unrolled, when they are unrolled you do not see any of those, but when they are not unrolled you see like this. When they are unrolled you see what you are seeing on the screen, right, like this. And then every unit or every state you should do the operation of what we have done earlier. The error for the entire duration t is obtained using this relationship. Okay. So, that means the error is summed across. So, every one that you find here they are summed, and then the error with respect to those parameters should be minimized. Okay. So, that is the actual aim of this back propagation through time. All right. So, this has to be continued until we reach a state where there cannot be any more updates possible. We are able to do the back propagation through time in this fashion. Once the neural network settles, we will stop, or when the error becomes very small we stop, or when the error does not change beyond a point we stop. Again, if you look at this parameter, when this becomes smaller and smaller, the confusion in terms of what is the pattern that I want to identify, within the network. I am talking about network looking at the patterns, right. The confusion for it is going away when the value of E becomes smaller and smaller. Okay. So, that is what we call it as perplexity. So, when this becomes smaller, we know that the network now has a lot of confidence in terms of identifying or predicting the next word if you are using it for natural language processing application. Okay. So, let us take a look at what this is in terms of the probabilities. I am sure you remember this, right. Probability of predicting this word I given I minus 1, or this is for the bigram, right, and this is for the trigram. And then if you use a character based model that we are looking at right now, let us say I am going to be looking at the 10th character and I want to predict the 10th character. So, in this model what we are actually computing is this, correct. This is what we are computing. So, in order for you to compute this and then identify that the machine has a lot of confidence in terms of predicting the right value, we need some kind of a mechanism to measure that, right. So, and that is what we use here. So, it is very similar. What we are here finding is nothing but right. This is what we are trying to find out. So, once the prediction is right, we move on to the next job, correct. So, the perplexity is computed using this formula. The lower the perplexity, better it is. All right.